For our final project, we implemented a relativistic ray tracer in order to simulate the imaging of black holes under specular and diffuse lighting conditions. From a high level, we are trying to simulate the bending and color shifting that light rays undergo when in the presence of massive gravity sources like black holes. We accomplish this by modifying the ray tracing code from Project 3, changing the BVH intersection routine to instead perform numerical integration using 4th order Runge-Kutta in order to obtain physically accurate black hole images. The curves are constructed of linear piecewise rays that connect the start point to the integration point. In these photos, we can see the 3 specific astronomical features we expect out of a physically accurate simulation. There is spherical distortion as the black hole moves through the scene, and the space warps accordingly. We also see gravitational lensing as light is focused on different areas of the scene, with the back wall of the bottom photo being the best example of it. Lastly, we also see ghost imaging inside the Einsteinian circle around the black hole, where the scene is inverted near the black hole's edges. We also implemented Doppler shifting by upgrading the RGB spectrum representation to a discrete spectral intensity map. We used 76 wavelength channels spanning the visible spectrum to achieve this. This is necessary because in an accurate physical simulation, light is redshifted when traveling away from gravity sources and blue shifts while moving towards one. Here we can see 2 more examples of the redshifting as the black hole redshifts the light of the entire scene. Note especially how the floor, bunny, and light all exhibit extreme redshifting upon contact. In this picture we can see how light is defocused in the glass ball and how there is redshifting in the background wall of the mirror ball. This shot is particularly interesting because the light reflecting off the mirror is warped by the black hole and reflected again, causing the mirror to be seen inside of itself. Here we see the secondary bright spots the black hole causes in the scene. Why is this topic interesting? Well, we tackle 3 big topics introduced in the course, and those being numerical integration, ray tracing, and color. We learned through this project that 4th order Runge-Kutta gives much better results even with large Runge-Kutta step sizes. Furthermore, color is difficult to implement with just RGB, as red shifts out of the visible spectrum, green remains in the spectrum, while blue becomes more green.